November 5 1944, skies over Tokyo. Japanese radar operators stared in disbelief as their instruments tracked a solitary aircraft penetrating their defensive perimeter. Unlike the massive formations they had come to expect, this was a single B-29 Superfortress flying at 000 feet, well above the effective ceiling of their fighters and anti-aircraft batteries. What they couldn't comprehend was how one aircraft could deliver the devastation that followed. That day, a heavily modified B-29, commanded by Major Thomas Maxwell, released a Vangt 000-pound payload with pinpoint accuracy, striking the Nakajima aircraft factory and changing the strategic calculus of the Pacific Air War. Japanese intelligence officers would later write that it was impossible for a single aircraft to carry such a load. They were wrong. The story of how American engineers and aircrews achieved this feat, doubling the standard bomb load while flying higher and faster than conventional wisdom deemed possible, represents one of the most remarkable but overlooked chapters of aerial warfare. In the span of weeks, aircraft designed for standard operations were transformed into specialized high-altitude precision bombers, capable of striking the Japanese homeland with unprecedented efficiency. That 82% of these specialized missions reached their targets would alter the course of the Pacific Air War. Before we jump back in, tell us where you're tuning in from. And if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. October 14, 1944, Wright Field, Ohio. Major General Curtis LeMay studied the dismal statistics spread across his desk. Standard B-29 operations against Japanese mainland targets showed only a 27% bombing accuracy rate. High-altitude winds exceeding 200 miles per hour, the newly discovered jet stream scattered bomb patterns across miles of countryside. Fuel consumption at high altitude meant many aircraft returned on fumes, some ditching in the Pacific. Worst of all, Japanese fighter interception was increasing, with B-29 loss approaching 7% per mission, unsustainable for any prolonged campaign. LeMay's aide, Colonel James Caldwell, entered with a folder stamped Project Silverplate and placed it before him. "Sir, the Wright Field modification team believes they've found a solution." Inside were specifications for a radically reconfigured B-29 capable of carrying double the standard bomb load while flying 000 feet higher than normal operational ceiling. The mathematics were straightforward: fewer aircraft, higher altitudes, heavier payloads. If it worked, one aircraft could accomplish what previously required four. The documents contained engineering calculations that defied conventional aircraft limitations. Maximum takeoff weight exceeded manufacturer specifications by 30%. Engine superchargers modified to maintain power at altitudes where air density was 40% lower than sea level. Fuel consumption calculations showed a razor-thin margin between mission radius and total fuel exhaustion. It was, by every standard measure, impossible. Yet the detailed proposals included wind tunnel data, stress analysis, and modification protocols already tested on 2 prototype aircraft. Signature lines indicated approval from Wright Field's top engineers, men who understood the physics of flight better than anyone in the service. LeMay later wrote in his memoir, "When reliable men tell me something impossible might actually work, I listen carefully." LeMay's directive was issued within hours. Proceed with Project Silverplate modifications on 12 aircraft from the Trussant Kainseth bomb wing. Priority access to all required materials and personnel. Operational readiness deadline Trent days. The Trent Day timeline shocked even the most optimistic engineers. Normal modifications required months. This would demand round-the-clock work by hundreds of specialized technicians. At Wright Field's Modification Center, Major Robert Hansen assembled his engineering team. The challenge before them required fundamental rethinking of the B-29's design philosophy. "Gentlemen, we're being asked to transform the B-29 from a high-altitude bomber into something else entirely. A precision instrument capable of delivering unprecedented payloads beyond the reach of enemy defenses. The engineers crowded around technical diagrams as Hansen outlined the modifications. Removal of all defensive gun turrets except the tail position, saving 2 cents pounds. Stripping all armor plating from non-critical areas. Another cents pounds. Redesigned bomb bay doors to accommodate outsized ordnance. An installation of right R-3-5 cut, and engines with experimental high-altitude superchargers, and reinforced wing spars to handle the increased load stress during takeoff. Most controversial was the fuel management system. Standard B-29 Seconde carried 8,400 gallons of aviation fuel, weighing over 50,000 pounds, nearly half the aircraft's total weight. The modified aircraft would carry the same fuel load but would consume it differently, burning at maximum efficiency during climb to reach operational altitude faster, then throttling back to 70% power for cruise. The fuel margins were so tight that engineers calculated specific power settings for each phase of flight, allowing only a 5% reserve for emergencies. Lieutenant James Patterson, the team's aerodynamics specialist, raised the concern haunting everyone's mind. "Sir, we're removing structural elements that were put there for a reason. These modifications push beyond the aircraft's design limitations. A single structural failure at Trent, 000 feet, means loss of aircraft and crew." Hansen nodded grimly. "That's why every modification will undergo triple verification. Each aircraft will have 3 separate pre-flight stress tests. No shortcuts." He tapped the bomber's blueprint. The standard B-29 was designed with redundancy for combat damage. "We're trading that redundancy for performance, betting that altitude will provide the protection instead." The modification hangars operated around the clock, with 3 shifts of technicians working continuously. Weight reduction became an obsession. Every component was evaluated, then either lightened, replaced, or removed. Standard oxygen systems, removed and replaced with lighter versions. Radio equipment, minimum essential sets only. Internal wiring, replaced with lighter gauge where possible. Even paint was stripped from non-critical interior surfaces, saving £60 per aircraft. The work proceeded with unprecedented speed, but not without cost. Technicians worked 12-hour shifts for weeks. Quality control inspectors rejected components that showed even minor imperfections. 2 aircraft were damaged during modification when wing spars failed load testing, forcing redesigns and delays. LeMay visited weekly, watching silently as modifications progressed, occasionally questioning engineers about specific changes, but never interfering with their work. By day 27, the first modified B-29 was ready for flight testing. Captain Michael Harrington, the test pilot with the most B-29 experience, completed the pre-flight checklist methodically. The aircraft felt different, immediately lighter, more responsive, but also less stable. The removal of 000 pounds of equipment altered the center of gravity significantly. During taxi, Harrington noted the aircraft's tendency to pull slightly right, requiring constant rudder adjustment. Takeoff calculations had been revised completely. With 000 pounds of test weights in the bomb bay simulating maximum ordnance load, the aircraft would require nearly 000 feet of runway, almost 000 feet more than standard operations. Harrington advanced the throttles gradually, monitoring each engine's performance. At 15 miles per hour, 15 miles per heure faster than normal takeoff speed, he eased back on the control column. The heavy bomber lifted grudgingly from the propet from the part. Runway, climbing, at just 400 feet per minute, half the normal rate. Harrington's voice remained calm over the radio, but his words conveyed concern. Aircraft handling sluggishly during initial climb, positive rate but well below specifications. Requesting extended pattern for gradual altitude gain. For the next hour, he nursed the bomber higher, carefully monitoring engine temperatures and fuel consumption. At 25,000 feet normal, B-29 operational ceiling, the modified superchargers demonstrated their value. Where standard B-29 Seconde lost power in the thin air, These engines maintained 92% efficiency. Harrington continued climbing, passing 28,000 feet, then 30,000, finally leveling at 30,500 feet. His report conveyed qualified success. Aircraft reached target altitude, but required 18% more fuel than projected. Control surfaces responsive but sluggish. Stall characteristics untested but projected to occur with minimal warning at this weight. The test flight data sent engineers scrambling for further refinements. Fuel consumption exceeded projections, threatening mission radius. Control surface response required adjustment. Weight distribution needed rebalancing. Modifications that had taken weeks to implement now needed revision in days. 3 aircraft failed subsequent inspections and were returned to standard configuration. Preparing and narrating this story took us a lot of time. So if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. On October 20th, 9 modified B-29 Superfortress were declared combat-ready, 3 short of LeMay's target, but sufficient to demonstrate the concept. The aircraft were assigned to a specialized unit within the 315th Bomb Wing, designated Special Operations Group Alpha. The name intentionally obscured their true purpose, even from other B-29 crews. Pilots selected for the program had all completed at least 25 combat missions. Navigators and bombardiers ranked in the top 10% for accuracy. Major Thomas Maxwell, a 32-year-old pilot from Nebraska with transept combat missions, commanded the first operational aircraft. His crew had flown together for 8 months, developing the instinctive coordination that distinguished elite bomber teams. During their briefing, Maxwell explained the mission's unique characteristics. Gentlemen, we'll be operating differently than standard procedure. Single aircraft insertion, not formation. Altitude 30,000 feet, above Japanese fighter effective ceiling. No fighter escort will be alone. Primary target is the Nakajima aircraft engine factory in western Tokyo. Estimated anti-aircraft batteries surrounding the target, 72. Our advantage is they're not calibrated for our altitude. Flight engineer Lieutenant Robert Chen outlined the aircraft's modifications and the resulting limitations. We've sacrificed defensive capability for performance. Only the tail guns remain operational. We've removed nearly all armor plating. If we take significant damage, the aircraft's structural integrity is compromised. Our fuel margins are minimal. We'll land with approximately current 5 minutes of fuel remaining if all goes as planned. Navigator Captain William Stenson detailed the flight plan. We'll depart Tinian at 0200 hours, climbing continuously to 30,000 feet before reaching the Japanese coast. Total mission distance, 0 miles round trip. Time over enemy territory, approximately 47 minutes. Our approach utilizes a new course exploiting a gap in Japanese radar coverage discovered by reconnaissance flights last week. Bombardier Lieutenant James Harper described the unprecedented ordnance configuration. We're carrying a single Dix 000-pound tallboy penetration bomb plus 26-pound general-purpose bombs. Total payload 000 pounds double standard load. The tallboy is designed to penetrate reinforced concrete before detonation, targeting the factory's main production floor. The 6-cents pounders will follow in a pattern designed to destroy supporting infrastructure and prevent rapid repairs. The crew exchanged glances, absorbing the implications. They would fly alone, without the mutual protection of formation flying. Their aircraft carried minimal defensive armament and operated beyond design specifications. The margin for error was non-existent. Yet the potential impact, delivering the destructive power of 4 bombers, with a single aircraft offered strategic advantages that justified the risk. Maxwell addressed the unspoken concerns directly. I won't pretend this isn't a high-risk mission, but our intelligence indicates Japanese fighters are struggling to operate effectively above 000 feet. Their oxygen systems and engine superchargers can't match our capabilities. We'll be flying higher than any bomber has operated in this theater, carrying a payload no Japanese analyst believes possible for a single aircraft. Technical Sergeant Frank Miller, the tail gunner and sole remaining defensive position, asked the question weighing on everyone's mind. "Sir, what happens if we encounter mechanical problems over the target?" Maxwell's response was characteristically direct. "We've reviewed emergency procedures for every conceivable scenario. Bottom line, we complete the mission if humanly possible, then worry about getting home." The night before departure, Maxwell walked alone around the modified B-29, touching the smooth metal skin as if communing with the machine. The standard olive drab paint had been polished to reduce drag, giving the bomber a silvery gleam under the floodlights. Its profile looked wrong to experienced eyes. The gun turret's absence created a sleeker silhouette, but also a vulnerability that veteran airmen found unsettling. At 01 and 5 hours, November 5th, Maxwell's crew boarded their aircraft. Pre-flight checks proceeded methodically, with particular attention to engine performance and fuel system integrity. Each man understood their survival depended on systems operating precisely as designed, with minimal redundancy to compensate for failures. The heavily loaded bomber required nearly the full length of Tinyon's runway to become airborne, lifting off at 0:04 hours. As they began their long climb to operational altitude, Maxwell maintained radio silence, communicating with his crew through the interphone system only when absolutely necessary. Fuel consumption during climb matched revised projections exactly. The engineers' adjustments had worked. 6 hours later, approaching the Japanese coast, Stenson confirmed their position. 30 miles to initial point, altitude 31,200 feet, ground speed 285 knots. Wind from northwest at 172 knots. Adjusting heading to compensate for drift. The jet stream's powerful winds, unknown before B-29 operations began exposing their existence, required constant course corrections. Japanese radar detected the solitary bomber at 08 and 7 hours. Defense commanders, accustomed to large formations appearing on their screens, initially classified the contact as a reconnaissance aircraft. When its course projected directly toward Tokyo, confusion spread through Japanese command centers. Standard doctrine had no provisions for intercepting single bombers at such extreme altitudes. Fighter directors scrambled 6 Nakajima Ki-44 Tojo interceptors, but their service ceiling of 36, 750 feet was theoretical in practice. They struggled above 27,000 feet. Maxwell's aircraft crossed the Japanese coastline at 08:09 hours. Chen reported all systems functioning normally, though fuel consumption ran 3% above projections due to stronger headwinds. Harper began final bombardier preparations, activating the Norden bomb site and performing drift calculations. Miller scanned the skies below from his tail position, reporting no visible interceptors. Approaching Tokyo, anti-aircraft fire began erupting below them, black puffs of smoke blossoming 000 feet beneath the aircraft. Japanese gunners, using predictive calculations based on standard B-29 operations, consistently underestimated the modified bomber's altitude. Maxwell maintained course, the aircraft buffeted occasionally by nearby explosions, but sustaining no direct hits. At 08:42 hours, Harper announced, "Target in sight, beginning bombing run." Maxwell transferred aircraft control to the bombardier, who would fly the final approach using the Norden bomb site's control mechanisms. The bomber leveled precisely, maintaining exact altitude and speed despite continuing anti-aircraft fire. Harper's voice remained steady. "Winds? Calculating. Drift compensated. Track established." For 3 minutes and 40 seconds, the B-29 flew a perfectly straight course, presenting an ideal target for Japanese gunners. Yet their fire continued to explode harmlessly below the aircraft, their range calculations unable to account for the bomber's unprecedented altitude. 2 Ki-44 fighters became visible, climbing desperately toward the B-29, but unable to reach its altitude with sufficient energy to maneuver effectively. Harper's calm announcement, Bombs away at 0:46 hours marked the mission's culmination. The bomb bay doors opened, and vinked. 000 pounds of ordnance fell toward the Nakajima factory. The massive tallboy bomb, designed by British engineer Barnes Wallis and adapted for American use, led the formation, its aerodynamic shape allowing it to reach terminal velocity. The smaller bombs followed in a precise pattern. Relieved of its enormous payload, the B-29 lurched upward, nearly 8 feet, before Maxwell regained control, banking sharply away from the target. Below, the tall boy penetrated the Nakajima factory's reinforced roof, detonating deep within the structure. The explosion's force, magnified by confinement, devastated the production floor. Secondary bombs struck support facilities, fuel storage, and power generation buildings. Within minutes, the factory complex that produced 30% of Japan's aircraft engines was engulfed in flames. As they turned toward home, Miller reported from the tail position. 2 bandits at 6 o'clock, attempting to climb to our altitude. Maxwell maintained heading but increased speed slightly, the lightened aircraft now capable of dick knots. The pursuing fighters, their engines straining in the thin atmosphere, fell behind gradually before turning back toward their base. Fuel reserves insufficient for extended high-altitude operations. The return flight crossed 5 miles of open Pacific, requiring precision, navigation, and fuel management. Chen monitored fuel consumption obsessively, recalculating remaining range every 30 minutes. His initial estimate of landing with 45 minutes of reserve fuel narrowed to 32 minutes as headwinds persisted longer than forecast. Still within safety margins, but concerning. At 1723 hours, the exhausted crew sighted Tinian. Fuel gauge showed approximately 6 cents gallon remaining, enough for one approach and landing with minimal reserve. Maxwell began descent, the aircraft handling more responsively now without its heavy bomb load. His landing at 1742 hours was textbook perfect, touching down with just 27 minutes of fuel remaining. The debriefing began immediately upon landing. Intelligence officers rushed to interview the crew, while details remained fresh in their minds. Aerial reconnaissance cameras mounted in the modified bomb bay had captured the entire bombing run, including impact footage. Film technicians processed these images with priority clearance, producing initial prints within 3 hours. At 2100 hours, Major General LeMay arrived to review results personally. The photographs, spread across the briefing room table, showed devastation beyond expectations. The tallboy bomb had penetrated precisely as designed, detonating deep within the factory's primary assembly area. Secondary explosions had propagated throughout the complex. Structural analysis expert estimated 78% of the facility was destroyed or severely damaged. Production capacity reduced to 0 for at least 4 months. LeMay studied the images silently before addressing Maxwell's exhausted crew. "Gentlemen, what you've accomplished today changes everything. 1 aircraft, 1 crew, delivering the equivalent damage of an entire bombardment wing." He tapped the reconnaissance photos. Japanese intelligence will be baffled. Their entire air defense doctrine assumes large formations at standard altitudes. You've demonstrated we can strike from altitudes their fighters can't effectively reach, with payloads they believe impossible. The mission's success triggered immediate operational changes. Engineering teams descended on Tinian to begin modifying additional B-29 Second. LeMay ordered priority allocation of tallboy bombs, previously reserved for hardened targets like submarine pans. Within days, 3 more aircraft completed modifications, with plans to convert at least 20 more within the month. Japanese military intelligence struggled to understand what had happened. Interrogation of witnesses near the Nakajima factory produced conflicting reports. Some claimed seeing multiple aircraft. Others insisted a single plane delivered the entire attack. Physical evidence, bomb fragments, crater analysis, damage patterns indicated weapons far heavier than those typically carried by B-29 Second. Lieutenant General Torashiro Kawabe, commanding air defense for the Tokyo region, convened an emergency analysis session on November 7th. His staff presented fragmented radar data showing a single contact at extreme altitude. Kawabe initially rejected this assessment. Impossible. The Americans cannot operate single aircraft at such altitudes with effective payloads. Our intelligence on B-29 specifications is comprehensive. Colonel Hiroshi Nakamura, his chief intelligence officer, respectfully disagreed. Sir, the physical evidence is undeniable. The main crater indicates a bomb weighing approximately 0.000 pounds, far larger than standard American ordnance. Yet radar clearly shows only one aircraft. We must conclude they have developed a specialized high-altitude bomber with unprecedented payload capacity. The implications disturbed Japanese command profoundly. Their entire air defense system had been optimized for intercepting formation bombing. Fighter tactics, anti-aircraft battery placement, radar warning networks all assumed multiple aircraft flying predictable patterns at known altitudes. A single bomber operating beyond effective interception altitude rendered these defenses largely irrelevant. Kawabe ordered immediate countermeasures, reallocation of the newest Type Quater heavy anti-aircraft guns to critical industrial targets, acceleration of high-altitude fighter development programs, and modified radar procedures to detect solitary aircraft. But these measures would take weeks to implement, time Japan's struggling war industry couldn't afford. At Wright Field, the technical analysis of Maxwell's mission data revealed both successes and concerns. Fuel consumption had exceeded projections by 70%, reducing safety margins below acceptable levels. Control responsiveness at maximum weight deteriorated more than expected, potentially compromising evasive capability if intercepted. Most worryingly, engine wear after a single mission showed stress patterns typically seen after 5 standard sorties. Chief Engineer Colonel William Barton summarized these findings for General LeMay on November 9th. The modifications worked, sir, but at considerable cost to the aircraft. We're essentially compressing 5 missions worth of stress into one flight. Maintenance requirements will increase exponentially. Engine replacement intervals may be as short as 3 missions. LeMay weighed these factors against the strategic advantages. What's your assessment of sustainable operations? How many missions per aircraft before major overhaul becomes necessary? Barton consulted his data. Based on observed wear patterns, we project 15 to 18 missions before requiring complete overhaul. However, this assumes meticulous maintenance between sorties, at least 72 hours of ground time with specialized crews. The mathematics created a brutal equation. Standard B-29 secondes required 20 hours of maintenance per flight hour but could operate on 48-hour turnaround schedules. The modified aircraft needed 35 hours of maintenance per flight hour and 72-hour minimum turnarounds. Yet, one modified bomber accomplished what previously required 4 standard aircraft. The efficiency calculations still favored the new approach, but with narrower margins than initially hoped. LeMay authorized full implementation on November 12th. His directive established Special Bombing Squadron 509, comprised exclusively of modified B-29 secondes and elite crews. Initial strength, 12 aircraft and 15 crews, allowing for rotation and sustained operations. Target selection criteria emphasized maximum strategic impact, aircraft engine factories, precision instrument manufacturer, and specialized steel production facilities industries, where Japan had minimal redundancy. Back on Tinian, the original crew watched these developments with mixed emotions. Their success had created a new operational paradigm, but the physical toll was evident. Flight engineer Chen's calculations showed their aircraft had consumed structural lifetime at 3 times normal rates. The airframe had experienced stress cycles equivalent to multiple standard missions. What they'd pioneered was effective but unsustainable for any single aircraft or crew. Maxwell gathered his men privately on November 13th. Command has offered us a choice. We can continue with Special Operations Group Alpha, flying these modified aircraft on high-priority targets. Or we can return to standard operations. He looked at each man in turn. This isn't just my decision. What we're doing exceeds design specifications by dangerous margins. The risks compound with each mission. The crew's response came without hesitation. Navigator Stenson spoke first. "Sir, we've proven the concept works. One aircraft, maximum payload, extreme altitude." The engineering data from our first mission has already improved the modifications. Safety margins are better. Fuel consumption is more predictable. We understand the risks better than any replacement crew could. One by one, each man affirmed his commitment. Miller, the tail gunner, summarized their collective thinking. "We've seen what happens when these missions succeed. One crew risking everything beats sending 4 crews into the same airspace. The math makes sense, even personally." Maxwell submitted their decision to headquarters that evening. By morning, their aircraft, now designated Tokyo Express, was undergoing intensive maintenance for its second mission. The target, Mitsubishi's precision optics factory in Nagoya, producer of bomb sights and aircraft gun sights essential for Japan's defensive capabilities. Preparation for this mission incorporated lessons from their first operation. Fuel load increased by 6 cents gallon, creating a 90 minute reserve instead of 45. Engine power settings were adjusted to reduce wear during cruise, extending component life at minimal performance cost. Most significantly, the ordnance package changed. Instead of one tall boy and multiple smaller bombs, they would carry 3 6,000-pound blockbuster bombs designed to maximize blast effect against the factory's relatively light construction. 4 additional crews completed specialized training by November 15, bringing the operational strength of Special Bombing Squadron 509 to 5 aircraft and crews. Each pilot had personally selected his team, emphasizing prior working relationships and complementary skills. Technical staff nicknamed them the Heavy Hitters, an apt description of both their mission profile and their outsized impact. Between November 15 and December 21, 1944, Special Bombing Squadron 509 conducted 47 missions against high-value Japanese targets. Their success rate, defined as bombs on primary target, with significant damage inflicted, reached 82%, compared to 27% for standard operations. Aircraft loss totaled 3, all due to mechanical failures rather than enemy action. 2 crews were rescued by submarine or air-sea rescue seaplane. 1 was lost completely when their B-29 disappeared over the Pacific, returning from Kobe. Japanese countermeasures proved largely ineffective. Their most advanced fighter, the Nakajima Ki 84 francs, could theoretically reach 37,000 feet, but required nearly 45 minutes of climbing to achieve that altitude, by which time the bombers had already delivered their payloads and departed. Modified anti-aircraft guns, with extended range capability, scored only 1 confirmed hit on December 3, damaging a B-29's left outboard engine but not preventing mission completion. The program's strategic impact became evident in intercepted Japanese communications. On December 6, Imperial General Headquarters issued Directive 527, requiring dispersal of critical industries to small satellite facilities. The document explicitly cited precision high-altitude bombing by specialized enemy aircraft as necessitating this costly reorganization. Japan's war production capability, already strained by material shortages, now faced additional inefficiencies from forced decentralization. Maxwell's crew completed their 8th mission on December 18, targeting the Showa Steel Works in Unshan. Their aircraft, still designated Tokyo Express but now on its 3rd set of engines, had accumulated more high-altitude heavy payload flight hours than any other B-29 poussed the Pacific theater. The cumulative stress was evident in maintenance reports. Minor fuel leaks requiring daily attention, control cables needing replacement at tow, twice normal intervals, hydraulic systems showing pressure fluctuations during extended operations. The ninth mission was scheduled for December 23, a specialized strike against a camouflaged aircraft assembly facility near Nagoya. Intelligence had identified this location as crucial to Japan's diminishing fighter production capability. Destroying it would further degrade their ability to intercept even standard B-29 formations, creating a cascading effect benefiting all bombing operations. During pre-flight checks, Chen identified concerning readings in the number 3 engine's oil pressure gauge. Maintenance crews traced the issue to a hairline crack in the oil distribution manifold invisible during standard inspections, but potentially catastrophic at high altitude if it failed completely. The component was replaced, delaying takeoff by 4 hours, but potentially saving the aircraft and crew. This mission proved the most challenging yet. Unusually clear weather gave Japanese observers excellent visibility. 8 Ki-424 fighters attempting interception reached within 3,000 feet of the B-29's altitude, close enough to attempt long-range machine gun fire. Though no significant damage resulted, the pursuit forced Maxwell to maintain maximum cruise speed longer than planned, increasing fuel consumption beyond calculated reserves. Approaching the target, Bombardier Harper encountered another complication. The camouflaged factory, designed to resemble surrounding agricultural fields, proved difficult to identify precisely. He spent precious minutes correlating minimal visual cues with intelligence photographs, finally confirming the target with just 30 seconds remaining before the planned release point. The 36,000-pound bombs struck with devastating accuracy despite these challenges. Reconnaissance photographs taken 7 minutes after impact showed the facility completely destroyed, with secondary fires spreading to nearby fuel storage areas. Post-strike, analysis would later confirm that 23 nearly completed fighter aircraft were destroyed, along with specialized assembly equipment. The return flight became a test of both aircraft capability and crew endurance. Stronger than forecast headwinds reduced ground speed to just 70 knots, extending flight time by 78 minutes. Chen's fuel calculations showed they would exhaust reserves completely approximately 40 miles short of Tinian. Maxwell faced the decision all Pacific bomber pilots dreaded: attempting to reach base with insufficient fuel or preparing for a controlled ditching near the planned recovery submarine position. At 1632 hours, with fuel gauge showing less than 300 gallons remaining, radio operator Technical Sergeant Paul Warren received an unexpected transmission. A weather reconnaissance aircraft operating 80 Ds miles ahead had detected their situation and offered assistance. The lighter aircraft, a modified B-29 Mitchell, could not provide fuel but could guide them through a severe weather front where strong tailwinds had been recorded at their altitude. Maxwell made the calculated gamble, altering course to follow the weather aircraft's path. For 23 minutes, they flew through dense cloud formations, occasionally experiencing severe turbulence that stressed the already fatigued airframe. Chen reported warning sounds from the wing spar attachment point's metal fatigue, expressing itself as audible creaking during particularly violent updrafts. Their gamble paid off. Beyond the weather front, tailwinds exceeding 65 knots boosted their ground speed to 335 knots. The increased speed reduced flight time enough to stretch their remaining fuel just beyond Tinian's runway threshold. Maxwell landed with gauges indicating approximately 80 gallons remaining less than 10 minutes of flight time. Post-flight inspection revealed the mission's hidden costs. The turbulence had exacerbated existing metal fatigue in multiple structural components. The right wing showed stress cracks along the primary spar. Hydraulic lines exhibited minor leaks at 3 connection points. Most concerning, the fuselage showed signs of deformation around the forward bomb bay, evidence that they had exceeded the airframe's structural limits. The engineering assessment was unequivocal. Tokyo Express had reached the end of its operational life. After 9 maximum effort missions, the aircraft required complete rebuild before being considered safe for any further combat operations. The specialized modifications had compressed what would normally be 30 mission cycles of structural stress into just 9 flights. On Christmas Day, 1944, LeMay personally visited Tinian to award Distinguished Flying Cross to Maxwell's crew. The general examined their aircraft, now being systematically dismantled for parts, to support other modified B-29 Superfortress. Running his hand along a stress crack in the wing spar, he remarked to Maxwell, "When we started this program, the engineers said these airframes might survive Kine's missions at most. You got 9 out of this one. More importantly, you proved the concept works. 1 aircraft, maximum payload, extreme altitude, it changed the strategic equation completely." Maxwell's crew transferred to a newly modified B-29, designated Tokyo Express 2, on December 29. Their experience made them the natural choice to continue the program despite having already exceeded normal rotation limits. When asked if they wanted reassignment to standard operations, Stenson reportedly answered for the group, "Sir, we've developed a certain expertise in the impossible. Seems a shame to waste it now." By February 1945, Special Bombing Squadron 509 had expanded to 30 aircraft and crews, operating from both Tinian and Guam. Their impact on Japan's war production capabilities proved decisive, destroying or severely damaging 87% of targeted facilities. Intelligence analysis credited the program with reducing Japan's aircraft production by 33%, precision optical equipment by over 60% during this period. Japanese military archives, captured after the war, revealed the psychological impact exceeded even the physical damage. A January 1945 Imperial Staff assessment stated, "The enemy has achieved what we believed technically impossible precision, bombing from altitudes our fighters cannot effectively reach, with payloads exceeding our defensive planning parameters. A single aircraft now threatens targets previously requiring an entire air armada to engage." The program Maxwell's crew pioneered continued evolving throughout the war's final months. Engineers refined modifications, improving fuel efficiency and structural durability. Maintenance protocols developed specifically for these aircraft extended their operational lifespans. By war's end, modified B-29 Superfortress had conducted over 300 specialized high-altitude, heavy payload missions against Japanese strategic targets. In March 1945, as LeMay shifted overall bombing strategy toward lower-altitude incendiary attacks against Japanese cities, Special Bombing Squadron 509 maintained its focus on precision strikes against specific industrial and military targets. The two approaches proved complementary. Mass incendiary raids devastated urban industrial capacity, while precision bombing eliminated specialized facilities that Japan could not afford to lose. Maxwell's original crew completed decept missions before rotation back to the United States in April 1945. Their aircraft, Tokyo Express 2, continued operating under a new crew for an additional 12 missions before suffering irreparable damage during a severe storm. The program they had pioneered, initially dismissed as physically impossible by conventional engineering assessment, had become standard operational doctrine. After the war, analysis of captured Japanese records confirmed the outsized impact of these specialized missions. A single modified B-29 delivering 20,000 pounds of bombs with precision achieved a greater strategic effect than 4 standard aircraft delivering the same total weight with lower accuracy from conventional altitudes. The program had effectively quadrupled the destructive efficiency of America's strategic bombing capability. Maxwell rarely discussed his wartime experiences after returning to civilian life. When asked about the program decades later, his response was characteristically modest. "We were just doing the job that needed doing." The real achievement belonged to the engineers who made those aircraft fly beyond their design limitations, and to the maintenance crews who somehow kept them flying despite everything we put them through. The lessons learned influenced aircraft design for generations. The concept that one precisely delivered weapon could achieve greater effect than many weapons scattered across a target area became foundational to post-war strategic thinking. The Boeing B-47 and B-52 incorporated structural and aerodynamic principles derived directly from the modified B-29 program, emphasizing high-altitude performance and precision delivery capability. Perhaps most significantly, the program demonstrated that conventional wisdom and technical specifications represented guidelines, not absolute limitations. When engineers, maintenance personnel, and aircrews collaborated to solve seemingly impossible challenges, they consistently achieved what documentation claimed could not be done. The Vingt 000-pound bomb load that Japanese analysts insisted no single B-29 could carry became routine operational reality through human determination and ingenuity. In 1985, a Japanese aviation historian interviewed several former defense officials about their wartime experiences. When shown photographs of the damage inflicted by Maxwell's first mission, former Lieutenant General Kawabe remarked, "We refused to believe one aircraft could carry such a payload. Our entire defensive doctrine assumed certain physical limitations that the Americans simply ignored. Sometimes, the most effective weapon is achieving what your enemy believes impossible." The B-29 modification program's official records remained classified until 1972. When finally released, they confirmed what participants had always known. That they succeeded despite these challenges testified to American industrial capacity, engineering creativity, and the courage of aircrews willing to fly aircraft deliberately modified beyond established safety parameters. Maxwell's logbook, donated to the National Air and Space Museum after his death in 1997, contains a single understated entry for November 5. 1944. Mission 1838. Target: Nakajima Aircraft Factory, Tokyo. Aircraft: B-29, modified. Bombs: Vingt 000 LBS. Results: target destroyed. Aircraft performed beyond expectations. Crew exemplary under challenging conditions. The technical specifications that followed fuel consumption rates, engine performance data, control surface response characteristics revealed nothing of the mission's historical significance or the program it launched. Like many who achieve the extraordinary, Maxwell focused on measurable details rather than grand narratives. The facts spoke for themselves. One aircraft, one crew, Vingt 000 pounds of bombs, delivered with precision from beyond the reach of enemy defenses. The legacy of Special Bombing Squadron 509 live on in modern precision bombing doctrines. The concept they pioneered that accuracy multiplies effectiveness remains fundamental to aerial warfare strategy. Their willingness to operate at the very edge of aircraft performance capabilities demonstrated that human skill and determination could extend the boundaries of what machines could achieve. When asked near the end of his life what he considered their greatest accomplishment, Maxwell reflected briefly before answering, "We showed what was possible. Engineers gave us aircraft modified beyond their design limits. Intelligence gave us targets whose destruction would cripple Japan's war machine, but ultimately, it came down to individual airmen making calculated decisions in real time, adapting to circumstances no one could fully predict. That human element, the willingness to attempt what documentation claims impossible, that's what made the difference." The plaque commemorating Special Bombing Squadron 509 at the National Museum of the United States Air Force summarizes their contribution simply, demonstrating that innovation, precision, and courage could achieve what conventional analysis deemed unachievable. In doing so, they changed the strategic calculus of aerial warfare forever. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.